So, hi. So I received a sign that I think means go. So I'll start. OK, well, thanks everyone to be here. It's good to see at least a few people we have not been working on this project attending. So Subra and I will be presenting today work have been going on at Microsoft on reservation-based scheduling, or sort of a way of getting Yarn cluster to support deadlines or SLAs for your production jobs. This has been collaborative work with a lot of other people. In particular, Jalal Difala was our intern, Chris Douglas, that most of you already know, Raghu Ramakrishna, Shriram Rao, and Ishai Menash. And all these folks are in CISL, the Cloud and Information Services Lab. Let me just give you context so you have an idea of how we came to this. We're a research group. We're embedded in the product side of Microsoft, and we're doing a lot of open source. I'll give you a second to process this. It's a little weird. So the key idea is, being a research lab, we have a lot of freedom of sort of chasing a little bit of like more speculative kind of projects. But we work very closely with product teams, so we usually focus on problems that are very relevant in what we see, and we can sort of confront with the reality of our products. And at the same time, we do a lot of open source. So everything you're going to hear in this talk is today part of Hadoop 2.6 is released. You can pick it up. You can, with one or two configuration parameter, can start playing with it. And I hope you will. And if you have questions for us, please ask. And in particular about questions, ask them as we go. It's much nicer and much more fun for us and for you if we get a little interactive during the talk. So please feel free to interrupt at any time. So what is the motivation for this work? Well, we're all after kind of the same thing. If you run big cluster, really what you want is to be able to run your production workloads, ideally together with your best effort or testing workloads, together in one cluster and get really awesome utilizations. And if you do this, really what you're after is to get very good latency for the best effort jobs. I'm calling best effort jobs those sort of small interactive jobs are submitted by data scientists or engineers that are exploring, testing new ideas, trying out new algorithms, exploring the data. And for this job, there is someone sitting at a console waiting for the answer, so you really want good latency. You want a 1 minute job to be submitted, getting through the cluster quickly, get the answer quickly. On the other side, ideally, we would like to run on the same cluster also our big production jobs. These are usually taking large amounts of data, are often periodic, and we wanted to run them with a good deadline. These jobs need to run and need to complete, have certain SLAs. We heard from the Yahoo guys presenting yesterday about how they cope with all this reality in practice, how they try to get good SLAs by tweaking all the parameters and what are the best practice. And I think it was a perfect pitch for the work we've been doing, right? This is exactly the reality we're faced. And of course, it is fundamental for us to get the cluster utilization up. We want to get good return on investment on this big, expensive cluster we're all buying. And so we want to run a lot of production jobs, a lot of best effort jobs, running the cluster hot, and ideally getting good latency and good production deadline for the production jobs. So, OK, so why do we need anything more, right? Yarn today or yesterday, before we've done this work, was not enough. Well, the problem is, it goes as follows, right? All of the modern resource management framework, and I'm including Hadoop, Corona, Mesos, Cosmos, Borg, all of the sort of big data framework out there, more or less have a notion of resource manager or scheduler. Vary a lot in the shape and form, but they pretty much all agree to have like some component that is deciding who's running where. And all of these frameworks provide a really nice notions such as capacity or fairness or application priority, user limits and user quotas that allow us to sort of instantaneously enforce certain invariants, right? And these are usually globally defined, they're fairly statically defined invariants, and we instantaneously enforce them, right? So we guarantee that, for example, a 30%, 70% split between two tenants is enforced at any moment in time. And this is all nice and dandy, but the main problem is that the schedulers are seeing the production job and the best effort job getting in through the same channel. Right? They look the same, right? They're, maybe are submitted to different queues, maybe are submitted with different priorities, but the system doesn't really understand the real difference that one set of jobs care about latency and the other set of jobs cares about finishing by a certain deadline, right? So here are the problems that, the three alternatives, all of which are pretty bad, that we can do today, right? We can try to say, well, let's try to give a very high priority to our production jobs. In this case, it's the blue one with a P on it. So these jobs are going to be run earlier or going to be given more resources. And so, say they get submitting this little simple example, basically get run right away when it's submitted, and it's definitely going to complete by the deadline, which is what we want. But the small best effort jobs, those interactive small jobs, will end up being stuck behind it, and will get really bad latency. So even if those jobs were submitted and they were very small, they're actually going to be run much later after this head-of-line queuing is resolved. And of course, this high latency is pretty bad. So the alternative is saying, well, let's try to do, for example, more of a fair allocation of resources between these jobs, give higher priority to the small guys, and these guys are going to be very happy. As soon as they're submitted, they're going to get the little bit of resources they want. They're going to go through the cluster really quickly. But if we have enough of those guys, they're going to push out our production job all the way until missing the deadline. And that is really, really bad, right? So we have some production jobs with deadlines which literally have a monetary amount that we have to pay as a fine to our partners if we don't deliver on time. So we definitely don't want to get into this space. So in practice, what everyone ends up doing is to carefully trading and doing these trade-offs and usually compromising a little bit on the utilization so that we have enough capacity to guarantee that the production guys will meet their deadlines and the best effort guys are being run in time. But of course, low utilization in this, tens or hundreds of $1 million clusters is not something we can tolerate. So we're going to improve on this. So here's the high-level idea of how we're going to improve. We're going to try to teach the resource manager about time. We're going to try to show the resource manager that there is a difference indeed between the best effort jobs and the production jobs. The production jobs have a notion of time embedded in it, a notion of finishing by a certain deadline. In particular, what we're going to do is the best effort job guys are going to go through pretty much the same channels they always did. They're going to be submitted. They're going to run in some queues. The scheduler will do what it does today. But for the production jobs, these are important. They're periodic typically. So they're going to declare in advance how much resources they're going to need. So they're going to, before they actually get submitted, maybe hours before, they're going to say, hey, I will need 500 CPU hours, sometimes between 3 and 6 p.m. Can you run me? Our system is going to leverage this flexibility, like this elasticity that has been expressed, and we're going to use a plan, I'm going to give you more details on this, to figure out, can I actually run you or not? And if I can, I'm going to plan ahead for what I'm going to do into the future, and I'm going to set aside some resources for you to run. And of course, at some point, we need to actually schedule this job and actually get resources, and we're going to make the existing scheduling frameworks a little bit more dynamic. What we're going to do, we're going to dynamically tweak those invariants that the capacity scheduler and the fair scheduler are really good at enforcing, but we're going to dynamically tweak them so that we can get the two things we want, good latency for the best effort jobs and guarantees SLAs for the production jobs. Again, feel free to interrupt at any time. So let's try to go through this a little bit more systematically. The first step is for the client to submit what we call a reservation request. This is pretty much a description, a declarative description of what I want. And I'm going to describe a little bit the language in a few slides. So this is done through an extended version of the application client protocol. If you have 2.6 running in your cluster today, or any future version after 2.6, this is part of the available APIs today. So the user asks for this at reservation time. So before the job is actually submitted, ask for this reservation request. The second step is for an object that we call a planning agent, which is sort of a piece of algorithmics, if you want, to find a place for this guy to run. To do this, we maintain a plan, which is, if you want, an agenda of how the cluster is going to be run into the future. Right? So we're maintaining a fully explicit way of how we're going to run, which job are planned to be run when. This is, again, only for the production job. Best effort guys are just flowing through on a side and on regular queues. But for the big important guys, we maintain this plan. And the planning agent is going to do, think about beam packing. It's going to try to find a good place where to fit this guy. Is this enough? Well, it is not, right? Because I could show up and ask for the entire cluster forever. And if I'm the first guy that shows up, a planning agent will tell me, sure, why not? There is room. Take the entire cluster forever. So we actually want to provide the notion of sort of a sharing policy, or some way of sort of enforcing some rules of the land and deciding that, well, you might not be able to get the entire cluster forever. Maybe you can instantaneously grab a lot, but over the integral, we want to limit how much you're going to get. Right? So it's going to be, Subra was going to describe this in more details, but it's pretty much the ideas of sort of a capacity over time, if you want, like some extension over time of the notion of capacity. So once this is all said and done, if we succeed at finding a good place and the user has the right to actually run in that amount of resources, we're going to give him back a reservation ID, or if you want, an airline ticket, right? A proof that the user has been actually accepted and has a reserved place for him to run in the cluster. OK, so far so good. We planned for everything. So how do we actually get it to enforce it? We introduce a new component, which is plan follower. This is a simple thread running inside the scheduler that takes information from the plan and publish them, in a sense, to the scheduler. So it's going to dynamically add, remove queue, resize them, do funny things to the scheduler based on whatever the plan says. So if I have a certain amount of capacity that is being promised to me, we're going to create queues, we're going to size them so that that capacity will be delivered at runtime to the job. And in fact, when the job gets submitted, presenting this reservation ID will be mapped to the right sort of structure inside the scheduler, and we'll get that amount of protected reserve resources to run, despite whatever is happening around him. Despite the fact that there are going to be lots of other best effort jobs running and jobs showing up at any time, that amount of resources protected is yours, you're going to get it. And this is how we guarantee that you're actually going to meet your SLAs. Of course, I describe a very blue sky picture in which everything goes according to plans. And if you run anything ever, you know that that's never the case, right? Our cluster keep on having machine dropping, estimates from user are wrong. So we need to be very adaptive. We need to be capable of sort of adjusting our plans, adjusting the way we run on whatever craziness happens inside the cluster. And right now, I'm drawing all of these as a single teeny tiny box that says adapter. In practice, of course, this is implemented as a bunch of different features around, and Subra is going to give you a bit more details on how this works. So, yes, please.
So does this interact with reservation, interact with preemption at all?
It does. It has to, right? Because the idea is, the question was, how does this interact with preemption, right? So we need preemption to be able to enforce any of this, right? So if I set aside a certain reservation, assume you ask for 100 containers, and I set aside that at 3 o'clock you're going to get 100 containers between 3 and 4 o'clock, and you actually do show up at 3 o'clock and you ask for all the 100 containers, I want to be able to give these containers to everyone else up until that moment. And in that moment, for example, best effort jobs, but the moment you show up and you actually have the right to get this container, preemption inside the scheduler will kick in, and it will sort of kill someone else or gently ask to preempt first, and if they don't preempt, actually kill them, so that you actually get your resources. So preemption is indeed a very necessary ingredient in this. OK, so the question, repeating the question is, what happens if multiple applications ask for the same time slot? Right? So of course, if they just fit, because I have 1,000 machines available and both ask for, say 100 and 200, of course, they both fit and they're both going to be scheduled. If they don't fit, the user express in the language that I'm about to show you, there's a fair bit of elasticity. So it's possible that I can just move around reservation, still respecting the constraint that the user gives me and fit them. And of course, there's a possibility that this just doesn't happen, right? You're giving me, ask for too much resources in a too much of a contended period of time, and I will not be able to accept you. I will have to reject you. The good news is that this happens at reservation time, which is much ahead of when you actually run. So instead of being in this bad world in which you run, and oh, I'm sorry, I missed your deadline because there were not enough resources in the cluster, hours even before, maybe days before you actually are supposed to run, I will tell you, hey, at that moment in time, there's no chance you're going to grab 1,000 machines and run because the cluster is absolutely busy, right? So there's more work we should be doing on priorities and possibly having more important guys trumping less important guys. For now, we have the implicit priority that whoever comes first has more right than whoever comes later, right? In the future, we're working, actually, this summer, we're working on exactly some of these problems. But the idea is, again, having the same problems much ahead of time, and in terms of absolute resources and not these percentages and queuing and things like this, makes it much more easy for user to deal with. Because, for example, you can just go and ask your friend to remove his job so that you can run because you're more important. And you have hours to do this, and it's a much better place to be than just simply, oops, sorry, your deadline has been missed. Correct, yes. So all this beam packing is all fully fluid, allow arbitrary overlappings and all that.
So what happens when a job's running like in the second place?
We will get to that in several slides. Okay? So to give you a little bit more of the idea of the language allows you to express, we can have very, very simple reservation, right? And this can be a simple rectangle in which I say I want 100 machines, exactly in parallel 100 machines for exactly 1 hour. Sometimes in this time range, right? So there's one first level of flexibility, which is the time range you specify might be larger than the rectangle you ask for. The second level of flexibility is that the rectangle itself doesn't need to be rigid. So you can tell me I want 10 CPU hours with a parallelism sometimes somewhere between 2 and 20. So you can separately define minimum, maximum parallelism, the total amount of hours you want, and how long each one of the containers, or each one of the minimum duration of an allocation should be. So you can give me something as malleable as a MapReduce job, which is just like a arbitrary shaped with a certain area, or you can give me something very rigid like a giraffe job that requires gang semantics, which is exactly 100 machine in parallel for exactly 1 contiguous hour. And this is just the basic reservation. On top of it, we give you a few constructs to be able to connect together multiple base building blocks like this to describe sort of skylines or DAGs of various jobs. And with this, in practice, it seems that it covers all the practical use cases. Of course, expressivity of the language is subject of constant extensions. We're working in summer on a few more of these, but I think what we have for now covers all the practical cases. A common question, which is probably your question, is how the hell I come up with these RDL expressions? Well,
In production, how close are the reservation declarations to the truth?
Yeah, so this is close to this. Let me give these slides and attach an answer to that. The idea here is how do I come up with this RDL expression, right? Sure, I believe you. Once I give you this expression of how much resources I want, you can enforce everything underneath. Let's assume you believe all of that. How I come up with these RDL expressions? So I think there are a few classes of jobs for which it's pretty feasible, right? One, periodic jobs, right? If you're being running on top of the same data every day for 6 months, I have a lot of examples of how much resources you need to execute. And answering your question, the idea is I can oversize a little bit my reservation. So if you normally need 100 CPU hours, I can say maybe I'll give you 120. Like I will box you with a slightly too big reservation. And of course, there's going to be a little bit of wastage there. But the idea is if you compare with the wastage you get by dedicating me a queue to make sure I can run, which means an infinitely long allocation of this height, versus giving me this squared box around my job, maybe slightly oversized, the cost of this is actually pretty small with respect to our baseline. The second class are leveraging the framework semantics. We have a couple of collaboration going on with researchers inside and outside Microsoft on basically taking jobs, for example, Hive, and take the optimizer estimates of how much we're going to run and how many containers we're going to need, and extending them with a bunch of profiling, so taking individual UDFs, running them, and figuring out for how long a UDF that runs on this much data will run, and trying to basically get estimates. We get pretty good results. We have seen on production workloads 10, 15% error around the exact executions. Of course, this is subject of continuous work, so we need to get better and prove that works on arbitrary workloads and the most complicated cases. But again, leveraging the framework semantics can go a pretty long way. And finally, we heard several use cases both inside and outside Microsoft on using this RDL just as a provisioning tool. We don't necessarily need to have one reservation for one job. We can have a reservation associated with multiple jobs, right? So this means that you can use RDL, or this language to specify resources, just as a way of saying, hey, during the day, I want to give 80% of my cluster to the data scientists, to data science team. But at night, I need to run some production workloads, some big batch data crunching. So I'm going to give the data science team only 10%. And I'm going to do the complementary description for the batch workloads, right? So this is a way of just basically creating time-varying queues. You can basically describe arbitrary sort of shapes, like the LinkedIn guys were telling us about Samza, and Samza as this kind of like daily flows that grows and shrink, and so we can just describe the resources like this, and the remainder of the resources can be given with these high-level SLAs or strong promises to someone else, right? And this is actually pretty good. Does this answer your question? Okay. So now let's let me go, before sort of passing to the baton to Subaru and letting him get more into the details of how we do this in Yarn, let me give you a high-level idea that this actually works. This experiment we were running on a 256 node cluster, pretty beefy machines, 128 gig of RAM, 12-hour drive per box, 10 GB across all the machines, and we are running grid mix workload based on Yahoo, Facebook, traces, whatever information we had available to sort of size and shape the jobs and the arrival times of the jobs. And we're comparing Ryan, which is the nickname we give to our system, against the capacity scheduler. We have about 3,600 jobs an hour. And what we see here is, in the first graph on the left, I'm showing the percentages of jobs that have been accepted versus, and the percentage of jobs that meet their SLAs or miss their SLAs. So the nice thing is that the first column, which is the one of our system, there's no red, which means for all the jobs we accept, which are about 96% of this workload, by design, the workload was designed to stress this cluster, right? So it was a little oversized for the cluster. So we cannot accept all jobs. So for the 96% of jobs we accept, all of them meet their SLAs, which means all of them got all the resources they were asked within the capacity allocated. And the capacity scheduler doesn't have this admission control mechanism. As a consequence, accept all of the jobs, but then about 15% of those, again in this experiment, were not able to meet their deadlines, right? So by accepting a little bit more of the job, was not actually able to really deliver on all of the deadlines. And even if we run the capacity scheduler cold, meaning about half of the workload, we still get a few SLA misses. And this is because, again, there's a few jobs that specifically were oversized for this cluster. They couldn't possibly meet their deadlines, right? And so even accepting those jobs, even with a cluster was fairly underloaded overall, we couldn't actually deliver on that. The second graph shows how many best effort jobs we can crunch through the system. I normalize on the capacity scheduler, so capacity scheduler get 100%. We get about 15% more best effort jobs being run through these few-hour windows that we were doing experiments on using our system. And again, this is because we can trade off. We didn't accept some of the production guys, so we have a little more capacity. We're also using very aggressively preemption in this, so we can actually leverage the cluster with higher utilizations and get better results. The other important graph is to look at the latency. What I'm showing here is a CDF of the delta between our runtimes and the runtimes in the capacity scheduler. So the way to read this graph is anything on the left of the 0 is good news. It means our jobs are being run with better latency with us. Anything on the 0, same runtime. Anything on the right, worse runtime. So beside a few outliers at the top, about the majority of jobs run similarly, and about 35–40% of jobs actually get, best effort jobs get better latency for our system than for the baseline capacity scheduler. And this is because we are allowed to, since we understand when the big production guys need to run, we can give them resources later and run the best effort job guys earlier. And we do this somewhat dynamically. If I show you the same graph for the production jobs, I will show you that actually production jobs get much worse latency. And you're like, wait, are you crazy? Bad latency for production jobs. No, it's exactly what we want, because production jobs don't care about latency in this scenario, right? We're looking at production jobs that only care about SLAs finishing by a certain deadline. They're headless accounts, they're submitted automatically, no one is waiting for an answer. So if I finish it as soon as possible, or I finish it close to the deadline, it doesn't matter, provided it gets done by the deadline, right? So optimizing for that, we give those guys worse latency, but meet their SLAs, and give all we have available in terms of resources to the best effort jobs so they can get actually very good latency. And of course, overall, we drive the utilization. Again, this is an experimental settings in which we're pumping the cluster as hard as we could, so we get very, very high utilization, close to 100%. Before I pass the baton, any other questions on this? Yes. Absolutely not. It is not a substitution at all. It is, in fact, the idea is you have your set of queues. Possibly to start, the majority of your queues are going to be exactly what you do today. And you're going to take a little bit of your capacity. And you're going to say, for this portion of the capacity, I'm going to enable reservations. And this will be handled through all these mechanics I described. But the rest of the things you do are just the same. In fact, best effort jobs will always going to be run through regular queues and not through reservations. At least that's what we're thinking for now. Yes?
So there is a lot of database literature, right, on They have Tasm and all of that. So it seems like Yarn is a static to a certain degree allocation system. And then the databases, on the other hand, have a very dynamic system. You have different priority levels, and you can move jobs, between them and so on. And it seems like you're going kind of in the middle. Would you consider going to looking at what those guys do and doing something similar, where you have more of dynamic workload management across, like refinement queues within Postgres, things like that?
So I've done lots. I'm a database guy that just joined the big data world, right? So I'm fairly familiar with the database world, and none of the techniques that I've seen in that space are quite applicable to this class of problems in my mind. Maybe you can tell me later if you have in mind something different. In a sense, here we're going for very coarse-grained. So with respect to capacity scheduler, we're much more coarse-grained. We don't look at individual tasks. We don't look at individual jobs. We look at like over time, in average, large amount of allocations, how they're placed, right? So in a sense, we're moving. If the capacity, if what you're describing go even more dynamic, even more in, small-scale priorities on the fly, we're going towards like looking at long-term planning for large swath of capacity. I think using what we have to do micromanaging individual tasks and application will crash and burn in horrible ways. And the other way around, like just leveraging very dynamic instantaneous allocations usually lead to pretty bad results or at least worse results than what you can do if you have actually a clear understanding of the future and you can actually plan ahead. Okay, I'll pass to Subra.
Thanks, Carl. Can you hear me? Yep. Yeah, thanks. So I'll just talk about the Yarn implementation, a little more, get into the details of the Yarn implementation. So Carlo talked about the RDL and all its richness. So it is recursive and all of those. So, but we looked at the practical nature of applications. We looked at Hive, we looked at MapReduce, we looked at Taze, Uzi, and we simplified Yarn for Yarn. So looking at all of those aspects. So what we have in Yarn is 3 APIs. So the specification for a reservation is called a reservation definition. I'll talk about that now. And we have added 3 APIs in Yarn for users to submit reservations, update a previously submitted reservation, or delete a previously submitted reservation. And what is a reservation definition? It talks about the arrival. That's the earliest time when your production job is going to be submitted. It talks about the deadline, which is self-explanatory. And there is a list of reservation requests. What is a reservation request? It's very similar to the resource request in that it encapsulates the resource, which is your CPU, memory, and now soon I/O. And it has a couple of other additional attributes. One of them is the number of containers, which, like Carlo mentioned, is the maximum parallelism which your job needs. It has concurrency, which is the minimum parallelism for your job. So what happens is we try to schedule anything between what is concurrency to your number of containers if we try to find allocations. And now that we have a notion of time, you specify the duration. How long do you need this resource for so that your SLA is met, right? And because it's a list, we have an interpreter for the list, and we have implementation for 3 interpreters today. It's all. That means accept my reservation only if you can satisfy all the reservation requests which I have. It's just as long as I get one of them, I'm good to go. Okay, order, which is like I want these reservations in this particular order. This is mostly for Taze DAGs, your Hive queries, because you have different stages and you want them in order, and each of the stages have different resource needs. It's not a flat, so it's like a skyline, right? So that's the area. And once a user submits an RDL, we have an agent, a greedy agent to place, and the intuition is, it's very much like a Tetris game. You have given us a block, a skyline, we try to find a place in the plan to allocate you, right? If we find, we're all good. If not, we'll say sorry, right? And how do we do that? We do a policy of allocate late and run early. That is, we start from your deadline and try to find the earliest spot with a single scan of the plan till your start, and find the earliest spot where we can allocate resources for you within the constraints you have specified through the reservation definition. And what that allows us to do and to call out your reservation is active from your start time, from your arrival to deadline, but the allocation starts, for example, in this case, The allocation starts here, your reservation is active from here. What that allows us to do is actually anticipate work. So if your job gets submitted at the arrival time, and if the cluster has idle resources, you can scavenge and complete earlier. If not, we provide good latency for the best effort jobs. We let them go through till your allocation starts, from which time you are guaranteed those resources, right? This is very nice because it's very fast. It's just a single pass. And it's greedy because it doesn't change the rest of the plan. It's just like the Tetris game. You don't move around the rest of the block. You just, whatever block you have, you just try to find the gap, right? So it's pretty fast. So, but there are a couple of shortcomings to this. One is because we do a larger spot where we can find, for example, in this spot, somebody asks a question. If somebody else wants a reservation later in this time, there's no space in the plan to allocate now. And the other thing is, if you look at the stage A3 red, it has a large drop-off because your reservation ends at your deadline. And somebody asks what happens when you have stragglers also, right? So now what is going to happen is your reservation capacity is going to go down drastically, and that might result in preemption kicking in, right? So what we have done, the greedy agent is in 2.6. We're continuing to work to improve it with folks with collaboration with MSR. So what we're trying to do is a low preemption. It's what we call as a low profile greedy agent. So what it still does is greedily tries to allocate, but it does a slightly more flatter allocation, so that if we have later, we can accept more reservations, and also there is no the drop-offs are not so sharp, right? And I'm going to go over this, in the interest of time, I'm going to go over this pretty quickly. What we did is we evaluated against a linear programming solution, which is an optimal solution, which actually knows all the entire reservations of the world, can move around everything. It's like a Tetris where a new block comes, you can move around everything to fill in gaps, which is the most optimal, but intuitively you can see it's pretty costly because for a single reservation, you have to move around everything. And what we observed is, we'll share this, you can look at it later. The acceptance is much higher because you can move around, like you can do like a defragmentation or compaction, but it's pretty expensive, and as the number of jobs and the cluster sizes increases, they converge very fast. So above 1,000 nodes, it's kind of converges around the same acceptance ratio, but we run much faster. We run like at 100 milliseconds, we are able to place 1,000 reservations where the ILP takes up to an hour to do that because it's moving around everything, okay? So now we found a placement for you, but we still can't commit because we have to make sure that there is no violation of quota. So today, all the schedulers, fair share ensures fair share, capacity ensures user limits and quotas. So we have a similar notion of that. Because we have a notion of time, what we do is to ensure that there's a capacity over time. That is, so what we do is also check for your instantaneously, you don't exceed a limit, but and also your area, there is an integral over time, you don't exceed your quota, right? What this allows to specify is to say that it allows users to grab certain resources for some time, a large chunk, because they need it for the SLA, and then at other times they give out that capacity for others. So you can have like instantaneously of 30%, you're up to 30% of the queue capacity you can go, and over 24 hours we have a sliding window. So over every sliding window of 24 hours a day, you don't go over 10%, right? This is very efficient to implement because it's an order of linear scan of your plan, right? And now I'll talk about if we find an allocation for you and you clear the value, you're okay with the quota, we accept it and commit it to the plan, right? Now how do we enforce it during runtime? So somebody was asking, how does it work with the scheduler? We actually use the schedulers to enforce at runtime, right? Because there's a lot of interesting work happening there. We don't want to throw that away and start reinventing the wheel. So we reuse all of that. So in this is the plan. The one on the top is the plan, which has now, in this case, we have 3 accepted reservations. And the arrows that points to now, it's a time, because we have a notion of time now. And at the bottom, this is a scheduler, state of the scheduler at that instance of time, because scheduler is instantaneous. So what we have now is just to simplify, we have just 2 queues. We have production and ad hoc. And to turn on this reservation system is pretty simple. All you need to do is enable it in yarn site. There's just a Boolean flag, say reservation enable true. And then one of the queues, obviously in this case, production queue, say that in this queue, I want to make reservations. So it's, again, you just go to your scheduler XML file and say reservable is true. So in this case, we have made the production queues as reservable, right? And now when we move on to this time, there's a plan follower. It runs periodically in the scheduler. At this time, we have 2 reservations, R1 and R2. What it does is it looks at the plan and then goes dynamically creates the queues in the scheduler. So in this case, it creates two queues, R1 and R2, with 15% capacity for R1 and 30% capacity for R2. And in the next instance, because we have a skyline, the capacity is changed, we moved on to the next stage. So it changes the capacity, looks at the plan and updates the scheduler queue capacity. Now R1 has 10% and R2 has 35%. And at this instance, we have R3. And because we didn't allocate late and run early, so what happens is now we have the start time of R3, but we don't have an allocation for it. So it has a 0% queue created, and it can grab any free resources which is available. And in this instance is where the allocation for R3 starts. So now R1 has 10%, R2 has 30%, and R3, the plan follower, has updated the scheduler queues accordingly. At the next instance, it's the same with the plan follower, so it doesn't do anything now. At this instance, R2 has reached its deadline, so the plan follower just goes and deletes the queue for R2, right? And at this instance, R1 is also done, so it removes the scheduler queue for R1. And at this instance, R3 is also done, so it removes that. And in all of this time, ad hoc queue you can submit queues, jobs normally to ad hoc queues, just like you would do today without reservations. And even in the production, other than the reservation, the rest of the capacity is available for submitting directly as normal and using it. This allows you to kind of try this mechanism in place with existing deployments, do a slow migration if needed, etc. Right? Okay. So, and this is an ongoing effort. We are trying to come up with a visualization for the plan. So what this does is this shows all the reservations. There is a kind of aggregation here because we're synthetically generating it at the deadlines kind of. Otherwise, you will see a much better distribution. What we have is you can search by a specific reservation ID. You can search by user, what are the reservations for the user, or give a time ranges and tell me what are the reservations. This is quite useful because both for the user and the admin can actually see how the cluster is being utilized, the forecast of the cluster utilization. Users can see how their allocations for their jobs are actually happening to make sure the SLA meets or doesn't meet and tweak it around, right? So this is very close to being committed. Okay, all of this is now good if things work well, right? But in a distributed system, there are always going to be failures. How do you deal with failures? We actually classify failures in two classes, right? One is application or the user, where like somebody again asked a question, what if I do a misprediction, right? I'm not really, because I'm learning this as I go. How do I handle this? The actual thing is the trivial solution always is you over-reserve, right? You ask for more resources so that you have a buffer, you meet it, right? And what we also allow today already in existing system is once your reservation deadline is ended, you can continue as a best effort job, right? The plan follower can move you and continue as a best effort job. Or like I talked about, we have an update API. We said we have submit, update, and delete. What does the update do? It allows you to actually renegotiate. For example, if you're running a job and you're expecting to be at 95% completion, you're now really at 90%, you can say, extend my reservation by the 5% of what I asked originally. That's the update API. So, and what we would do then is kind of logically remove your existing reservation, try to place this new reservation and see if we can find a place. If so, we'll say, yes, we have updated. Otherwise, we just let the existing reservation run, right? That's one. And there's also the framework side failure, which is like capacity impairments, right? What happens if 10% of a cluster just goes down, which can happen, right? How do you do that? Again, the trivial solution is you don't actually allocate the entire plant, right? You have a buffer, you have a threshold headroom, so which is like 10%, so you may be able to deal with it. But sometimes, even if you have a buffer, you might have a large enough failure which is above the buffer. How do you take care of those, right? So what we have is we call it as replanning. So one is we try to move around the reservations at that time to make sure can we get it, or we actually might have to cancel reservations. That sounds very bad. It is, but it's not as bad also as it sounds, because today with the schedulers, if you have a 10% capacity impairment, everybody's job is affected, every queue is affected by the 10%. So potentially everybody's SLA could be missed. What we try to do instead is, because we are making absolute promises, so we try to find, if suppose we had 1,000 containers as the capacity of the cluster, and now we have lost 100, we try to find reservations with 100 containers and just cancel them, so that the others are not affected and they meet their SLA. So it's still better. And right now we have an implementation which we can do better by coming up with a cost for finding the reservations to cancel. What we have today is just based on acceptance times, first in kind of. So you're prioritized on your acceptance. Earlier you submit your higher priority. But we're also working on models which are better, which we'll talk about, just mention about. And what this cancelling also does, it's good because it gives a heads up. It's not like when you have a capacity impairment at 4:59 and your deadline is at 5, it's not like we just tell you now we don't meet your deadline, right? We are actually looking at in future and we'll actually give you a heads up. There is a capacity impairment, please look at it, try to do something, kind of, so yeah. In conclusion, what we do is we give SLAs for production jobs, and because we have a allocate late and run early policy, at the same time we improve the latency for best effort jobs, which consequence in high utilization for the cluster, right? Whatever we talked about, we have it in Hadoop 2.6. The umbrella Jira is Yarn 1051. So I'd just like to shout out to the folks who helped us get this done. Vinod, Karthik, Anubhav, Vangda, Jian, Sandy, Alejandro, and much more people. So they made sure that whatever we did is aligned with what is existing and things are working, because all of the systems are in production and they are to blame if things don't work too. So yeah, ongoing work. This is not like things are done. So this is a good baseline. There's a lot of interesting work happening. One, for example, the plan is today is completely in memory. So if you have a HA setup and your primary RM goes down, you lose all your reservations. So we are actively working to integrate with the HA mechanism. So that's the 2573 is the Jira for that. We talked about the low profile greedy agent. That's 3656. Both of those, we have a design proposal for both. The planner itself, we are trying to get in priorities or something to make sure that we pick on priority rather than acceptance time. So that is, we're thinking about it still. And one request which we get a lot, both internally, externally, is we like this. It looks like it can meet our SLA, but our production jobs are always recurring. We get this every day. So do you want us to make a reservation every day? Or we would rather try to make a single periodic reservation for our production jobs. So this is something we really want to take up. And another cool thing which developed in parallel was node labels. So we are trying to add support for node labels. And another proposal which we have just made is federating Yarn. So to scale out Yarn to like 100,000 nodes. So we need to play nicely there. So that's, yeah. So we have a lot of interesting work. We're looking for collaborators. Yeah, come reach out to us. Thanks, guys. Yep. Any questions? Yeah. Yep. Yeah. Yes. Yes. Yep. Yep. Yep.
Yeah, so you can absolutely, right? One of the interpreter of the reservation request that he described is order. So what you can say is, I need 200 machines for 1 hour, followed by 50 machines for 20 minutes, followed by 10 machines for 1 hour.
Oh, repeat the question.
And everything, the entire order list need to finish by 5 p.m. So we sort of work backward and try to find, where each one of these stages need to happen to make sure you get to the very end. Of course, if you were wrong in your estimates, things might slide. That's why we give you also renegotiation.
Yep.
So how is the framework support now? So the framework needs support summit that basic plan, not reduce.
Yep. Yeah. So I'll just to repeat the question. The question was, yep. So we need to wrap up. So last question. So the question was, what is the framework support needed? So for Spark, we've already added for MapReduce. It is a two-phase protocol now. You first submit a reservation, and then during the job submission, you just say the reservation ID. You get a reservation ID, and you specify that during job submission. We've already done it for MapReduce. We are in the process. We have already tested for Spark. We'll put it out soon. So that has to be added, and we are doing that. Yep.
Okay. So I guess we'll take
questions offline. Yep, because we are out of time.
Well,
Thanks, guys.